Uh, Now, in today's unit, we are really will be looking at some motor generator aspects, not in rotating machine, but first to give you a glimpse of the things. It is linear, a linear generator or motor in its simplest form. I will describe that. But before that, I will just want to tell you one thing very clearly. I expect that you know that, but very quickly I will tell. For example, these are the two rules which we will be often using. For example, if you have a conductor, okay, title I will write slightly later. Suppose you have a straight conductor, finite length, and it is moving with some velocity v, okay, and let there be a magnetic field present all along the plane of the paper whose strength is B into the paper. So, this cross is into the paper, velocity is like this. Then what happens, and the length of the conductor is suppose L. So, this is the conductor A B, let me avoid B, x y, and it is moving along this direction. Then what happens, between the two ends x and y, a EMF will be generated. The value of this EMF will be B L V, where B is the flux density, all along the paper it is there, you imagine. How this can be created? Perhaps on above the paper there is the north pole, and below the paper there is a south pole. So, lines of forces will be perpendicular to the plane of the paper, and your conductor is on the plane of the paper, and it is suppose moving with a velocity v, and then between these 2 points there will be an induced EMF whose value will be BLV. Okay. Now, the question is what should be the polarity of these voltages. So, if you apply, then you have to apply your right hand rule. You recall that your forefinger always will denote B, thumb will denote the velocity, and then this middle finger will give you, the tip of the middle finger will give you the plus sign of the voltage induced. For example, here it is like this, this is B. So, plane of the paper, this is V in this way V. So, the polarity of the induced voltage will be, this is the tip. So, this will be plus, this will be minus. Understood this? So, this is the tip of the middle finger, there I will write plus and below I will write minus. So, this voltage VLV is actually the potential of x with respect to y. See, always it is a good habit to write potential difference between 2 points. No point in telling E x, voltage at x, with respect to what, that is very important. So, potential of x with respect to y, put the numerical values here, you will get some number, that will be the voltage existing. And I can say that this thing is equivalent to as if there is a battery here, plus minus the value of the voltage is VLV. This point is x, this point is y. That is what I mean to say. If velocity is constant, B is constant, it will be a constant DC voltage. Product of all these things, inwards. Obviously, this also tells me many more things. Suppose L of the conductor is finite, fixed. If you reverse the polarity of the magnetic field, that is, instead of cross into the paper, if it is coming out, then this will become potential of x and y will become negative BLV, indicating that y is really positive, x is negative. Similar is the velocity. If you reverse velocity, similarly the polarity of the induced voltage will reverse. So, this is called EMF equation, which will be often used in any machine analysis problem, complicated machine. So, a conductor moving at a constant velocity v will be having an induced voltage, provided it is placed in a magnetic field B, and this B, direction of B and V, they are mutually perpendicular. This is into the paper, velocity is this way and B is this way, they are mutually at perpendicular condition, then only induced voltage will be there. For example, if this conductor is moved vertically in presence of this B, no way, there is no voltage, because you must have a perpendicular component of B with respect to V. If it exists, then there will be some induced voltage across the point. V cross B, they say, okay, V cross B. Anyway, let us not make things complicated, this you must understand. Okay. Similarly, if you have this conductor, same conductor of length L meter, all units are SI unit, this length is L, and suppose once again you imagine on the top there is a north pole, below the paper there is a south pole, permanent magnets, lines of forces will be there, and suppose it is present all along the place, then B, symbolically I am just showing one line, but all the lines of forces are present. So, suppose this length is L, and what I will do now, I will to this end I will connect some wires, 2 wires I will connect, flexible wires, and I will connect a battery outside source. Therefore, this will drive a current in this circuit. Okay. What will be the magnitude of the current? This voltage divided by the resistance of this path. So, some current I inject into the conductor. Conductor is X and Y. Now, we are in a situation, a conductor of length L is carrying a current, and there is a magnetic field perpendicular to the direction of the current flow, like this. Then what happens? This conductor is going to experience some force. Now, the question is, what is the magnitude of the force and what is the direction of the force? Like while we found out the voltage across x and y, 2 questions should be asked: what is the magnitude of the voltage and what is the polarity of the voltage? Similarly, when a conductor, I am telling it is experiencing a force, then I must say what is the magnitude of the force and what is the direction of the force. And the magnitude and direction of the force is obtained by Fleming's famous left hand rule. It was Fleming's right hand rule to find out the magnitude of the voltage and polarity of the voltage, and this is Fleming's left hand rule to find out the magnitude and force experienced by x y, because it is carrying a current and placed in a magnetic field. the magnitude of the force will be B, I and L. What is B? B is the flux density. What is I? I is this current, that is in this case I. And how to find out the direction? To find out the direction, what you have to do? You have to apply left hand rule, mind you. So, once again the forefinger is the direction of B, that is into the paper. This middle finger is the direction of the current, that is this way, and then thumb will give you the direction of the force. So, magnitude of the force is BIL and it will be towards right. Understood? Therefore, these two rules, that is Fleming's right hand rule and Fleming's left hand rule. Right hand rule is to be used to find out the polarity of the voltages, magnitude of the voltages, and left hand rule is to be applied when you want to find out the force, when a conductor is carrying current placed in a magnetic field. So, three things are required. A conductor is required in case you want to generate some voltage, you require some velocity of that conductor and you require some magnetic field. Absence of any of these three will not generate any voltage. Similarly, to generate some force. So, this is called motoring, as you can easily understand, somewhat like a motor, you get some motion, and this is somewhat like generator. You generate a electrical voltage between 2 points. So, this is the very fundamental thing. Now, after learning this, we will now go to a simple motor problem. Okay. What is a motor? The arrangement try to understand. Suppose you have, let me draw slightly in 3 dimension roughly. Suppose you have got 2 rails, railway track, frictionless, okay, and over which you have a finite length conductor, okay, and it is, of course, there are wheels. This conducting bar of length L is resting on the pair of wheels, and therefore, it can move this way or that way. If you pull it, it will move to this. So, these are rails. It can be moved. Now, you imagine above this track, railway track, above this track, you have a permanent north south pole, permanent south pole magnet. I do not know how to sketch it. It is like this. Some south pole magnet is above it, and below it there is a north pole magnet. Understood? So, this diagram, if you look from this engineer's way, if you want to draw, look from this end, it will then look like this. What I want to tell, there is a north pole, south pole above it, and this track you can see then only a line, railway track, and the conductor is section of the conductor, that is x y, this is the y side, this is the x side. y side you can see. Okay. If I look from this end, it will be y, this is south pole, and what I am telling, below this I have kept a north pole, such that the lines of forces exist all along the track. And what is the width of the magnets? Width of the magnet is the track length. Okay? North pole all above the track, south pole, and below the track it is there, and this is your conductor. So it goes like this. B. I mean this same thing I have drawn here in this example this way. Now, as I have told you, suppose I want to move this conductor with a velocity v from left to right. So, this velocity will look like this, it will be moving, and suppose the magnetic field starts from here. Before that, this conductor which is on the track was here, still moving velocity v, length of the conductor perpendicular to the paper. Will there be any induced voltage? No way, no induced voltage. V is there, length of the conductor is there, but there is no B. The moment it enters into this magnetic field region, then when it comes here, for example, it moves with a velocity v, with this end y, the other end I cannot see, that is x at the other side, it is like this moving. So, now the length of the conductor is this, B is this, velocity is this. So, polarity of the induced voltage BLV will be there definitely, and if you apply this rule, if you look from the top, the conductor length you can see here is y x at this point. If you look from the top plan of this view, and it is moving with velocity v, and then B it is dot here, is not. So, if you look from the top, you will see lines of forces going up. In this case, the voltage induced here will be BLV. Now, what will be the polarity of the voltage? Polarity of the voltage, to find it out, this is B, this forefinger is B in this diagram, B, this is V, and middle finger, they are mutually perpendicular, these three things. Tip of the swan, this will become plus, this will become minus, BLV. And this thing is equivalent to telling that the voltage is like this, and the magnitude of the voltage is this BLV. Now, let us imagine that this conductor is moving on a railway track where there is absolutely no friction, nothing. Therefore, tell me, if this conductor I say that is moving with a constant velocity v, how much force you need to keep the motion alive with constant velocity v? The answer is 0. That is what Newton says, that to move a thing against any friction with a constant velocity, no force is needed. If some force is applied, it will either accelerate or decelerate, that is different issue. But to move a body on a frictionless track, no force is needed, it will move. Initially, you have to give that push, whatever velocity it acquires, it will continue to move uninterrupted, unless somebody applies some opposite force it will perhaps start decelerating and so on. Therefore, a generator, and it does not violate anything, no laws of physics is violated, because work done by this conductor now is 0 and you do not require any work to be done either. Although this bar conducting length is having a kinetic energy associated with it, and the value of the kinetic energy will be half m v square, where m is the mass of that conductor. Okay, this is the thing. Therefore, that is a simplest generator. So, once again I draw it and write down this. This is suppose south pole continues forever. This is suppose north pole continues forever. What is the width? Width is perpendicular to the paper, that is finite width equals to the separation of the two rails. So, and this conductor is on the rail, it is moving with a velocity v, and here you will see the end y, the other side you will see the end x, and there will be induced voltage in it. Okay. Now, let us see the other operation. For example, what I will do in this diagram, which is not a very neat diagram, but you try to have the feel what I am telling. Now, suppose I have this conductor moving on the tracks present in a magnetic field, you get a induced voltage. Now, what I will do is this, it will be present in that magnetic field, but I will pass some current through this conductor by external means. Okay. So, this is the conductor. If you see from the top, this is the conductor. You can see the total length of the conductor if you look from the top. This is L length, okay. And where at the rail lines also you will be able to see in this view. From the top if you look at, you will see V, and B is of course dot all along the track. Now, what I will do, this track here I will connect a switch here with a flexible wire. This is the track, this is track, and I will connect a battery. This is B, and I want to pass current so that movement will be this way. So, let us see what happens. So, if you connect a battery to these rails, wheels always contact with the rails. So, circuit will be completed. If this is the polarity of the battery, then you are passing some current like this I through the conductor. Then if this is the current, this is the field, you see you have to apply left hand rule to know the direction of the force. It will be this way, force will be acting. B is coming out of the paper, B is coming out, and I is going like this. It will be like this way. So, what I will make it? I will make the polarity like this, plus minus. This is I. Then this is B, this is B, this is I, and then the force will be acting like this. Is that clear? So, B is coming out of the paper, I is going like this, and it will move in this direction. What is the magnitude of the force? Magnitude of the force is B I L. Therefore, conductor was stationary. In presence of a magnetic field, you pass some current I, it will flow like this through this flexible wire, it will complete its path, and then it will experience a force B I L. Now, as it starts moving, so what happens if you apply some force to a mass, it will accelerate. So, it will go on accelerating, velocity will change, but anyway it will move with a velocity. But one point must be understood very clearly, if it starts moving, the magnitude of the current, I am not sure whether this E divided by total R of the circuit will be the magnitude of the current. Because what happens, the moment this fellow starts moving, I know that a conductor moving in a magnetic field with some velocity will have some induced voltage in it. Therefore, this conductor itself will become another sheet of EMF. Therefore, to find out the currents in this circuit, not only this EMF will be acting when this conductor has started moving, but also another EMF which will be generated across the two points of this conductor. These two together divided by the impedance or resistance of the circuit should decide what will be the current in the circuit. Therefore, in this unit what I have done is this: if there is a magnetic field, if it is moving with a velocity v, there will be some induced voltage in it. Polarity of the induced voltage, how can you show? This is V. So, this will be cross. Cross means it is like this, is not? So, B, V, and it will be cross means the other end of the conductor will have plus sign. And if you have a conductor carrying some current I in this direction, and if it is having a B like this, then it will experience a force, the value of which I will get it from left hand rule. So, B I L, this is the direction of the force. And so, in this lecture, a single conductor moving in a magnetic field, what will be the induced voltage we have discussed, and we have discussed how to decide about the polarity of the voltage. Similarly, if a conductor which carries current and it is placed in a magnetic field, then it will experience some force. The direction of the force can be obtained by using left hand rule, and the magnitude of the force is B I L. So, in our next unit we will further carry on with this. Thank you.